Hi, this video is to explain atomic radius and trends that we see in atomic radius on the periodic table. So first off, the definition for atomic radius is going to be equal to half the distance between two atomic nuclei. Again, that's how we measure atomic radius because we cannot easily measure from the nucleus of the atom to the outermost electron. So we would describe it as being between two nuclei and then taking half that distance. So when we think about that on a particular atom, if we have the atom lithium, lithium has 3 protons and would have 3 electrons. So it has 2 electrons in the first shell and it would have 1 electron in the second shell. And so there is an attractive force between the 3 protons that are found in the nucleus and that outermost electron. And that would be called, or how we would describe that force is Coulomb's law, using Coulomb's law. So Coulomb's law is force is equal to Coulomb's constant times the charges, or the different charges, Q1 and Q2, over the atomic radius squared. And so what we're really looking at specifically, and what you need to kind of understand on Coulomb's law, is we need to look at the charges and how the charges relate to the distance. And so with lithium, we have 3 protons and the electrons there. And so there is a difference of charges between the nucleus and those electrons, and that affects the radius of our atom. If we look at another atom in the same period, and that would be, again, a period is a row on the periodic table, another atom of the same period, let's just say we choose carbon. Carbon has 6 protons in its nucleus, and it would have, a neutral carbon atom would have 6 electrons. And so we put 2 electrons in the first shell, and then carbon would have 4 electrons in the second shell. Now, because carbon has a greater nuclear force, with 6 protons relative to lithium having only 3 protons, when we go back to Coulomb's law, the carbon atom, the nucleus of the carbon atom, is being a larger positive charge, is going to be able to pull these electrons, these outermost electrons, in more readily. Now, both lithium and carbon, because they're in the same period, have the same S1 shell, right? They have the S1 shell. And so these electrons experience the same shielding effect. So the S1 electrons do have some impact on the overall nuclear charge, but both atoms would experience it equally. So again, carbon having more protons is going to be able to pull in those valence electrons more readily. And so we would see that pattern across the periodic table as we move from left to right across the periodic table. We have the same number of, within a period, we have the same number of electron shells, but we have an increase in nuclear charge. And therefore, as we move from left to right across the periodic table, the atomic radius will get smaller. And that's a trend. Within a period, the atomic radius gets smaller. Now, if we look at within a group, so we look at lithium. Again, lithium has 3 protons, and beneath lithium on the periodic table is sodium. And sodium has 11 protons. And so, again, like lithium, it has 1 electron in the first shell. In the second shell, it has 8 electrons. But unlike lithium, sodium has a third shell. And that third shell has 1 electron. And so what happens here is the addition of now a third energy level of electrons means that even though sodium has more protons than lithium, the shielding effect from now the 1s and the 2s and 2p subshells are going to result in the effective nuclear charge for sodium being equal to the effective nuclear charge on lithium, right? We would do 3 minus the 2, and lithium would have an effective nuclear charge of 1. We come down here, sodium, 11 minus the 10 non-valence electrons, that would have an effective nuclear charge on 1. So the addition of this extra electron shell or energy level means that sodium is going to have a larger atomic radius than lithium. And we would see this continue as we work down the alkali metals. We would see that potassium has now 4 energy levels or electron shells compared to sodium, so it's going to be larger. Rubidium has 5, so it's going to be larger than potassium. And we work our way down here, and we see that pattern, that same pattern, work anywhere on the periodic table as we go down a group. As we go down a group, we see the atomic radius increase. So as you go down, atomic radius increases. And as we go across the periodic table, atomic radius decreases. Because again, we have an increased nuclear charge with the same number of energy levels of electrons. And that's how we would explain the periodic trend for atomic radius. Thanks.